Is it? I know it's a PNG format or something.
Yeah, that's PNG. That's screenshot. So,
Yeah, it JPG will not. My
Sir,
handwriting will not
actually,
get.
your entire, I mean, our entire lecture has been, made into one single image, and it is difficult to actually read. Just that's the reason.
it's too much to zoom in.
So if I do video, that you are doing in where? You are doing in computer or mobile?
Yeah, in
Sir, on
computer.
the computer in VLAN.
Is it difficult? Yeah,
Yes,
anyway,
sir.
so
Actually, the image is
yeah, but if I
somewhat
do,
like blurred.
yeah, if I do PDF, will it be easier?
Yes, sir. Because I think we will get that picture
Yeah, we'll try.
quality. So
So we'll try. Has the recording started? Hello.
yes, sir.
Okay. So let me write down the Ehrenfest theorem that I wrote. So, and we will prove it today. So these are basically the expectation value whenever I am writing bracket with respect to any arbitrary function. So this is not a stationary state of the Hamiltonian or stationary state of anything. Right now the proof is on an arbitrary function. So all of you are familiar with this notation that this is average value. I'm not writing in a big way. So let me now expand it in the following manner. Psi star, so this is an operator A. These are all time dependent. The time dependence comes from the wave function now or the operator. Okay. And we have integrated over x. So it is of course function of time. So if I now take ddt of the average value, then there are three parts which are time dependent. So I will write each of them del psi star del t, x of t, a of t, psi x of t dx plus psi star del a del t, psi x of t, again, these are all dx, and then finally the conjugate of this term, which is psi star x of t, a of t, del psi of x of t, del t dx. So there are three terms that we have. Okay. Now clearly, when you look at the second term, this is an average value. This is an average value of del A del T operator. So that really gives you the first term here. So it's very easy. So we have to now analyze the first and the third term. So this now comes from the time dependent Schrodinger equation. So we have h of psi equal to IH cross del psi del T. Remember, this is a postulate. So it is true for any arbitrary psi. So I can now write del psi del T as 1 over IH cross H psi. Correct. And I can write del psi star del T, which is a complex conjugate, as minus 1 over IH cross psi star H. Note that this will be now conjugate. It is in reverse order. So I take psi star and then Hamiltonian.
So it should be T, right?
Yeah, T is there.
I mean del psi star.
Yeah. Sorry. So it is just psi star S. So I have to put this here in the third term and this one in the first term, right? This one in the first term. So that's all I have to do. I'll put it here and here. So if we now do this exercise, so the first term will have this. So it will have a minus 1 over H cross. I'm now writing all the term. Minus 1 over H cross. And then you have integral psi star H psi dx. So I have put this and psi star H, sorry, A has to be written. A psi dx. Okay. Then the third term would be plus 1 over h cross integral psi star, and now you will have a first, because I am writing for del psi del t, a first and then h psi dx. Correct? And then finally I am left with the second term, which is of course very easy to write, plus expectation value of del a del. Is it clear? I mean, in some order I have written, I have not followed the same order, but I hope you understand. So most important thing is to write this term and this term using the Schrodinger time-dependent Schrodinger equation, and then I immediately get the Ehrenfest theorem, as you can see, because now you can separate this out, del A del T, and then you write this as plus 1 over IH cross. You have now an average value of AH minus HA. Please note there is a minus here. So this is going to become average value of a commutator H.
Why is modulus sign being put in the?
What is the modulus sign? What is the modulus sign?
In del A, I mean from del A, del T also, and the commutator also.
This is the Dirac notation. No? Oh, sorry, I'm not put everywhere consistent. So
Okay,
Dirac
that's
notation is this is A is psi star. This is just a Dirac notation.
Oh, okay, sir.
There is nothing great about it. Sometimes I'm not putting consistently. That's okay. But anyway, so be that as it may, I have finally the Ehrenfest theorem that the average value of A, again, I'm not putting consistently, so don't worry. So del A del T, if I just write, that also makes the same understanding, plus 1 over IH cross commutator A with H average value. So that's your Ehrenfest theorem. That's a proof. I've already proved the theorem. It takes really 8 to 10 minutes. Now the important thing is the consequences of the theorem. So what do you learn from the theorem? One very important part that you already have done is that what happens if the psi, so A, if psi is an eigenfunction of the Hamiltonian. Remember, we discussed this and we know that this should be time independent. Let us also assume, for all practical purpose, that A is explicitly time independent in all these consequences. So I want to take that out of the equation. So that means this part is 0. Del A del T is not there. It is explicitly time independent. So I have only this term to deal with. So let us see what happens if psi is an eigenfunction. So let's calculate this term, psi star H minus HA psi dx. 1 by H cross is not a problem. Let me just calculate this. So you see the first term. Psi is an eigenfunction of H. So this will become H psi will act on psi. It will become E psi. So first term will be E psi star A psi dx. Is it okay with all? Because H, this is an eigenfunction of Hamiltonian. So of course, this will become E times psi. So you have psi star A psi dx. And then
So on the left one, they are acting in the reverse order. That's why
So
you're
this
taking
one
it.
H is acting on psi. This is acting on the reverse order. Right? So it will again become E psi star. So again you will get minus E psi star A psi. Is it clear? So in both cases, they will give the same result. Because H is either acting here or H is acting on psi star. And the result is E psi star. So when it is acting here, E psi star, and then here A psi. When it is acting on this side, it is E psi star A, then psi dx. Is it clear? So if psi is an eigenfunction of H, this integral is 0. The integral of the commutator of A with H is 0, and hence ddt of the average value of A is 0. for explicitly time independent operator, and that is something we already learned. So nothing new. I already told you that if it is an eigenfunction of the Hamiltonian, you have what is called the phase factor, and the phase factor cancels out when I take the average value, right? Out here. So obviously it is 0, so it's okay. But what is interesting is also we learn that what happens if psi is an eigenfunction of A. So again, I'm doing the same calculation, and you can see it should be identical. H and A are very same. If it is eigenfunction of A will act on psi to give a number times psi, or A will act on this side to give a number times psi. So what you will get here, let's say A psi is equal to small a times psi, then what you will get here is that integral H will become integral psi star A H psi dx minus sen A psi star H psi. I hope you agree. I don't have to prove it. Just like I did for H eigenfunction, I'm now doing for A eigenfunction. So what remains here is the integral psi star H psi. Because this is not an eigenfunction of psi. Psi is not an eigenfunction of H. So this will remain. And this, but the result is still 0. So what is interesting is something new we learn. Initially we said if psi is an eigenfunction of the Hamiltonian, every dynamical observable in that state is time dependent. Every ddt of A. But now we see that if psi is an eigenfunction of that operator, then also ddt of A is average value of A is 0. And that is not very surprising because it's an eigenfunction of the operator A. So when I make measurement, I will get the same values. And at different time also they remain the same. That's the important thing. So I get that from the Ehrenfest theorem. C. Next I get a very interesting corollary. If H commutes with A, right? Or A commutes with A, then automatically it is 0. So now I don't put a conditional psi, but I say that if my operator A commutes with H, then the commutator of AH is 0, and hence ddt of A is again 0. So look at the beauty. And in this case, it does not matter what is psi, irrespective of psi. In the third, simply because there is a much stronger condition that the operator itself commutes. Is it clear? Hello? Hello?
Yes, sir.
Yes, sir.
So I first proved the Ehrenfest theorem. I am telling you the consequences of Ehrenfest theorem is if the wave function is an eigenfunction of the Hamiltonian or the eigenfunction of the operator, or if the operator itself commutes, the average value of the operator A is time independent. So interestingly, when will it be time dependent? Now you have to exclude these three cases. So what is that cases? So when the operator will be time dependent, or when the average value will be time dependent, even though A is explicitly time independent. This of course we continue to write.
So can you please repeat the statement?
Yeah, now I'm asking, when will the average value of A be time dependent? We have seen that it is not time dependent. ddt of A is 0, A, B, C, right? If psi is an eigenfunction of A, psi is an eigenfunction of A, or A commutes with H. In either of these three cases, the average value of A is time independent, right? What does ddt of A mean? 0 means it is time independent, right? The average value does not change with time. Hello? Hello? Hello?
Yes, sir.
Yeah. So now I'm discussing when will the average value be time dependent? Even though A is explicitly time independent. So the case in point would be if A does not commute with H, that is number one. Because I have to exclude all the three cases.
And not even any eigenfunctions.
Yes, and A is commuted with H, and psi is neither an eigenfunction of A nor of H. You understand? So only in such a case, of course there will be several such cases, but only in such cases it will become time dependent. In all other cases, the average value of A will be time independent. Of course, I have assumed that the operator A itself is explicitly time independent. Otherwise, of course, one term will be there. And that will, of course, make it much more complicated, because how would Hamiltonian commute with A if A is time dependent? All right. So these are very important thoughts on the Ehrenfest theorem, where you tell when are the average value of A time dependent, and the time dependence part is very important. If you look at this A, B, C, in fact, the case that the quantum chemist will deal with is case A, when psi is an eigenfunction of H. Clearly, we don't have to bother. Group theory deals with this case C, that the operator commutes with H. This is where group theory will deal with. You will have a course later. And again, we don't have to bother, because all the symmetry operators commute to the Hamiltonian. So the symmetry operator average value is time independent. Okay? In all other cases, we have to worry about the time dependence. Okay? Is there any question? Otherwise, I'll close, because I have finished this part. And now what will happen is that we will go from the next class on the calculating psi as an eigenfunction of Hamiltonian. So our quantum chemistry will set it. So our quantum chemistry is to calculate this or to solve this equation. Now I have already told you this is a very minor part of the entire quantum mechanics. It's only solving time independent Schrodinger equation. And it is just to solve a condition when the psi will be an eigenfunction in the Hamiltonian. And now you know its significance. All other average value of the operator will be time independent. Energy, of course, will be time independent. So it's a very important part on different problems. So I think Professor Sen will come after the midterm exam. So we will also have a question on the midterm exam now. I will see that midterm exam is for how many hours? 1 hour?
Sure, 1 hour 30 minutes, I guess.
Okay. So I will see that we get sufficiently. Yeah, I understand the questions. If they have to be calculated, they become lengthy. But if they're conceptual, then there is no problem. Okay. So we'll try to see.
Excuse
No,
me,
sir,
conceptual
but
questions.
even sir, those conceptual questions needs some time, because we have to read that, we have to.
Just one
So-
minute. Can you just go?
Excuse me, sir. I had a question from the second one. So, do we still call them steady states even if the function is an eigenfunction of A?
Oh,
Of the
thank you.
operator?
Thank you. I was just there. Yeah. Thank you very much. Yeah. Okay, great. So we'll see you later. So, okay. Thank you. Bye bye. Yeah, sorry. Please tell me what you are telling. I had another meeting actually. Please tell me.
So, I was just asking if even if the function is an eigenfunction of A, do we still call it a stationary state or not? Or
Yeah, it is. It is a stationary
So,
state for many
there is
reasons.
no physically there is no difference between it being an eigenfunction of H or an eigenfunction of A.
If it is eigenfunction of A, energy won't be stationary.
Okay, so whatever is corresponding to that operator would be stationary, say momentum
So
or
in
angular
terms of
momentum or something like that.
yeah. And this is stationary for all other reasons that any other operator A will
Okay.
also be time independent.
Okay, so
That is very
for
special with the
something like
Hamiltonian, because A commutes with H. That is very special of the Hamiltonian.
so
The other-
something
yeah.
like Bohr's quantization condition would correspond to something like this B case, where we are having it being an eigenfunction of A rather than H. L
Bohr's
equal to ns by
quantization,
2 pi.
angular momentum. You're talking of angular momentum, right? Yeah.
Yes, sir.
So, but Bohr, that's an ad hoc theory. Don't even talk of eigenfunction, because when Bohr did the quantization, the concept of eigenfunction is not there.
Okay, sir.
1913, quantum mechanics is not there. So that will unnecessarily confuse. Okay, somebody was
Yes,
telling me
okay,
about
sir.
something about the questions. If it is conceptual questions, also the
Yes, sir.
Yeah.
Yes, sir. No,
What is
sir. Not problem, sir. I was just saying that if it was means if it is somewhat like conceptual question, then sir also it will need some time because to read the question and
Of course.
to and also to think for
Yeah.
means what would be and there and it gets more difficult when all the options are very close. So we have to decide that which
No, I
option
understand.
goes best.
I
So
understand.
sir,
I
yeah.
understand. I understand. I mean, typically my own estimate is that it takes little more than 2 minutes per question in MCQ.
Yes, sir. Yes, sir.
That's my
That's
typical thing. So when you told 20 minutes, I mean, that's my typical thing. So that's why I'm asking her, and I'm requesting you
Sir,
if you can take best 10 out of 20, best 10 out of 16. So 10 questions in 20 minutes is okay. Yeah.
Sir, I just had a question. I mean, we derived this mathematically that the derivative of expectation value of A is this thing.
Yeah.
In the interpretation is something like this, right? That we have, let's say, 1,000 identical systems. We are
Yeah.
measuring them at one.
Time.
We are telling
One
robots
time.
to measuring them at one
Yeah.
time
One
and
time.
getting and computing
Right.
the expectation value.
Right.
And
And
then at the
then,
next instant, again, we are measuring it.
yeah. So you
Set.
have to, it's a thought experiment. So you have to again create the same identical systems after, let's say, 5 minutes or 2 minutes. You calculate
Right.
the average
So,
value of it.
but
Then,
we cannot
then
make a second measurement also, right? So we have to wait for that time to elapse and to make the first measurement for the next instant, something like that,
right.
right?
So you have to again re-prepare, because I told you the Copenhagen interpretation. After one measurement, system changes, right?
Okay.
Every system is changing. So I don't want that system. I have to re-prepare the system
Okay. So I mean,
at another time.
we first prepare for the first instant, then we wait for the next instant
Wait
to
for the
arrive, and
right.
then
So
we measure it.
that state will evolve in time. The original state. So you have to go back to the original state and make it evolve with time.
Okay. Okay. Now I understand.
Okay. All right. So best of luck. Yeah. I will take care. Yeah, we'll see. So I think you also write to Professor Sen, because she is much more in touch with you than me. So you please write to her about this questions thing. I think for MCQ 2 minutes per question is actually good. But at the same time, she told that the highest mark was already 70, right? So it's not that everybody is doing badly. But in any case, I mean, I think you discuss that, what kind of thing will be there in the WhatsApp group. Okay? So let me stop the recording and come back. All right. So good luck to all of you for the exam. When is the exam?
So next Saturday.
Oh, next Saturday. So you have time to prepare. Okay, good. All right. So no problem. So I'm sure you'll do well. Thank you. Thank you. Bye. If any of you have questions, then you can still ask. Otherwise, goodbye. Okay.